For centuries, humanity gazed at the stars and made a fundamental assumption. We believed that our little corner of the cosmos, our solar system, was the standard model. We had a neat and orderly arrangement, a single star at the center, a set of inner rocky planets, a belt of asteroids, and then the gas giants orbiting further out. This configuration seemed so logical and elegant that we developed a beautiful theory, the nebular hypothesis, to explain its formation. It was a perfect story that neatly described everything we saw right here at home. This was the picture of the universe we held in our minds before we began to discover worlds beyond our sun. The moment we started finding exoplanets, that entire picture shattered. One of the very first types of planets we discovered defied all logic and expectation: the hot Jupiters. Imagine a planet. Now imagine a planet with the mass of Jupiter, a colossal giant of gas. Now imagine that planet not orbiting far out in the cold depths of space, but parked impossibly close to its star, 20 times closer than Mercury is to our Sun. When these objects were first detected, the scientific community was deeply skeptical. It made no sense within our existing models. How could a gas giant form so close to the searing heat of a star? The initial reaction was outright disbelief. The proof arrived when one of these bizarre objects was observed transiting its star, passing directly in front of it and causing a detectable dip in starlight. This confirmation forced a profound and humbling revolution in our thinking. We had to throw out the textbook and start again. The current leading theory is a violent and chaotic one. These hot Jupiters likely form in the outer reaches of their systems, much like our own Jupiter. But through gravitational interactions, a cosmic dance of instability, they are kicked inward. They get flung into wildly eccentric orbits that, over immense periods of time, circularize incredibly close to their parent star. While they are unusual, occurring in only about 1% of systems, their existence was our first major clue that our solar system is not the norm. The surprises did not stop with hot Jupiters. We soon found another class of world entirely absent from our own planetary family: mini Neptunes. These are planets that occupy the size gap between Earth and Neptune, typically about 2 to 4 times the radius of our homeworld. Our solar system has nothing like this. Is a mini Neptune a massive rocky planet, a so-called super-Earth? Or is it a small gas-enveloped world, a true miniature version of Neptune, perhaps with a vast global ocean? The astonishing fact is that this type of planet, which we have no example of here, appears to be the most common type of planet in the entire galaxy. Our solar system is missing the most ubiquitous planet in the universe. This strangeness extends to the planets we do have. Take Jupiter itself. This massive planet has played a crucial role in the history of our system, potentially shepherding material and influencing the development of the inner planets. Yet data from missions like Kepler, which has discovered thousands of exoplanets, suggests that only about 10% of Sun-like stars host a Jupiter-sized planet. Our system doesn't just have one, it has two, with Saturn being a gas giant in its own right. Furthermore, simply having 8 stable planets is itself a relative rarity. Many systems we observe have fewer planets, often packed much closer together than ours are. Even our Sun's solitary nature is unusual. We take it for granted that a star shines alone, but the cosmos prefers company. Approximately half of all star systems are binary, consisting of 2 stars orbiting a common center of gravity. Some are even trinary systems, with 3 stars locked in a complex gravitational dance. The nearest star system to us, Alpha Centauri, is a perfect example. It consists of Alpha Centauri A and B, a tight binary pair, and then Proxima Centauri, a red dwarf that orbits them both at a much greater distance. The dynamics of planets in such multi-star systems must be incredibly complex, with orbits that could be highly eccentric or unstable compared to our relatively placid and circular paths. This raises a profound question about our place in the cosmos. Is our solar system special? The evidence is mounting that it might be an outlier in several key ways. We orbit a stable single star, a G-type main sequence star, which is itself not the most common model. The most populous stellar class in the Milky Way is the red dwarf, small, cool stars that make up about 75% of the stellar population. Our Sun is in a minority. We have a full suite of planets, including a giant planet in Jupiter that seems to be relatively uncommon. And we are missing a mini-Neptune, the galaxy's most popular model of planet. The diversity of exoplanets tells a story of chaos and dynamism. It suggests that the formation of planetary systems is a violent, unpredictable process. The serene order of our solar system might be the exception, not the rule. This has direct implications for the search for life. Our system provided a stable, billion-year cradle for life to arise and evolve on Earth. If most systems are more chaotic, with planets being ejected, migrating inward, or experiencing intense stellar radiation from multiple suns, the number of stable, habitable environments could be far lower than we once optimistically hoped. Our understanding of how systems form begins in vast clouds of gas and dust, known as molecular clouds. These are the nurseries of stars and planets. Within these clouds, slight density fluctuations begin to collapse under their own gravity. As a region collapses, it spins faster, flattening into a protoplanetary disk. At the center, the pressure and heat ignite nuclear fusion, and a star is born. In the surrounding disk, dust grains begin to stick together, forming pebbles, then rocks, then planetesimals, and eventually planets. This is the nebular theory, and it remains our best framework. However, the devil is in the details. The precise mechanisms of how you go from microscopic dust grains to massive planets are still not fully understood. This is a frontier of modern astrophysics, involving incredibly complex supercomputer simulations that model the collisions, accretions, and gravitational interactions of trillions of particles. It is a chaotic and nonlinear process, and slight differences in initial conditions, the amount of material, the stellar mass, the presence of a nearby supernova, can lead to wildly different outcomes. An orderly system like ours, a system with hot Jupiters, or a system dominated by mini-Neptunes. When we look up at the night sky, we are not looking at a universe filled with copies of our solar system. We are looking at a cosmic zoo of planetary possibilities, a menagerie of strange and wonderful worlds that defy our earthly imagination. We built our theories from a single data point, our home. Now, with thousands of new data points, we see a universe that is far more creative, far more violent, and far more diverse than we ever dreamed. Our solar system, with its quiet stability and its life-bearing world, begins to look less like a common blueprint and more like a rare and precious jewel. This growing catalog of cosmic oddities forces us to confront a deeply profound and humbling possibility. The Earth may not just be unusual, but virtually unique. The concept of rare Earth suggests that the confluence of conditions necessary for a stable, life-bearing planet like ours is so exceptionally specific that it might be an extraordinary fluke in an otherwise barren and chaotic universe. We are not just looking for another planet with liquid water. We are looking for a planet that has maintained a delicate equilibrium for billions of years. Consider the chain of events that led to us, a stable, solitary star of the right size and longevity, the presence of a Jupiter-like giant in just the right orbit to act as a gravitational shield, deflecting comets and asteroids that might otherwise cause constant extinction-level events. Our large moon, likely formed from a cataclysmic impact in the solar system's youth, which stabilizes Earth's axial tilt, preventing wild climatic shifts that would render complex life impossible. The precise plate tectonics that recycle nutrients and regulate our planet's temperature over eons. Each of these factors is, by itself, not necessarily ultra-rare. But the probability of all of them and dozens more occurring simultaneously in one system and persisting in a stable harmony for over 4 billion years is astronomically low. It transforms the emergence of intelligent life from a near inevitability given enough time and space into a precarious 1 in a trillion long shot. The universe is vast, but its sheer size does not guarantee that this specific, intricate recipe has been repeated elsewhere. This leads to the unsettling conclusion that we might truly be alone. The Fermi Paradox, the question of where all the aliens are, may have a very simple and lonely answer: they do not exist. The great silence we hear when we listen to the cosmos is not because civilizations are hiding or have transcended. It is because there is no one else out there to call. We gaze at the countless stars, not as potential homes for other societies, but as beautiful, empty, and sterile nuclear furnaces. In this view, our planet is not just a pale blue dot, it is a sanctuary, a singular, fragile oasis of consciousness in a breathtakingly vast and silent desert of space. The absence of alien megastructures, signals, or visitors is not a puzzle to be solved, but the expected outcome of a universe where the ingredients for life are so impossibly scarce. This realization imbues our existence with a profound responsibility. If we are the universe's only way to know itself, then our mission becomes infinitely more critical. The preservation of our biosphere and our species is not just a local concern, it is a cosmic imperative. We are not just inhabitants of Earth, we may be the only sentient guardians of meaning in a silent, unconscious cosmos, and the only ones who can appreciate its terrifying and beautiful emptiness.